Hello everybody, my Bongo cat is acting. I noticed that it doesn't work, like Bongo cat doesn't move the mouse when I'm using my graphic tablet. So I'm so nervous to explain you about heat equation. We'll first consider 1D case to derive heat equation. It looks in this form. With some number alpha. First, let's imagine ourselves a tank filled with liquid, and imagine you've dropped some paint into this liquid. It will diffuse everywhere. Same thing happens when we heat up one boundary of like some parts of our surface. The heat will diffuse in same way, like these two systems are equivalent, and I want to use the paint example to explain you how to get this equation. Since we are considering 1D case, we have to work in 1D world. In x-axis we don't have y-axis since it's 1D, and imagine you have some rod. It has initial position x0 and final position x1. It has this length. We put a lot of paint from the initial position, and this this paint will move from high concentration to low part of concentration, like this. It will diffuse like this, and to find the total mass of our paint we have to sum up all dx's. Dx is just this unit, this small unit, infinitely small unit amount, the amount of unit at this point, dx's of our function from x0 to x1. Here u is a function that describes how our paint will move, will diffuse, to be precise. And here, what if I am interested how many dm, how many of amount of mass does this small unit, does this small, infinitely small unit of dx has at time dt. Since our mass depends on time, at this time there will be at the region when t is 0, we have mass equal to mass, and maybe when time is equal to some number, maybe mass will become 1/4 of the initial mass, who knows. So, and I want to know at time dt, how many dm amount of mass do I have at dx position. To find it, we have to take both sides by dt, partial derivative by dt. Since this mass depends only on t, we can write direct derivative by dt equal to 0 x1 u t xt dx. And let's recall the heat conservative energy, law of energies, conservative energy. Sorry guys, I have bad English. We know that how many let me describe it like this. If you have some rod, again, now let's for now forget about paint. Let's heat up one rod. What it will do, suppose this side is so cold, this side is so hot. This hot side will move towards the cold side, or in different words, like hot moves to cold, or in different words it means that the mass that moves from high concentration to low concentration is conserved, like yeah. So how we can write this flow in, flow out in our case? It will be x1 t, while at x1 position, 0 position at time t, and here while I'm taking derivative, partial derivative by x, like since it moves from x-axis on x-axis, I have to take I want to know the rate of change of the mass distribution by x. That's why I'm taking partial derivative of my function uxt by x. And well, suppose you have some wood and suppose you have some metal. If you heat up equally at the same location position, you know that metal will heat up so quickly and you can't touch it at all. If you heat up the wood, the heat won't distribute as fast and uniformly as metal. So you can't hold, for example, the top parts, opposite part of the wood, and your hand won't get too hot. This is because there is some constant proportional to our dm dt that decides how fast heat distributes along our material. Let's move it outside the braces. And here now I'm curious about how the mass, since this is paint, it has some mass. If we work with heat, we have to work with energy, but let's work with mass. Now I'm interested how mass, the rate of change of mass at the final position. I'm not interested how it will move along the material up to final position. So to get rid of this side, I have to find the rate of change of mass at x1. In other words, I have to take partial derivative by x1 at the final position. Since my dm dt is equal to this equation, I'm taking its partial derivative by x1, and I get the next formulation. Since I'm taking the partial derivative by x1, my x0 will disappear, and since my derivative is taken by dx, this is also dx, integration is cancelled by derivation, equal to alpha u. This part also cancels because it depends on this 0, x1t, or in other words, I get ut equal to alpha ux6. And here we have derived our equation. Next, I want to consider 3 boundary conditions. First boundary conditions is called Dirichlet's. Be easy. What it says in simple words is we are giving heat on all edges. This is 1D rod. It doesn't have thickness. It's 1D. This is, well, math is so abstract actually. Yeah. It's so hard to mention a 1D rod and just draw 1D rod. Okay. Or if you draw in 2D case, we have some surface metallic and we are heating up all the sides, giving heat to our system, to our material, and it will heat up. Same for 1D. In other words, we are giving a constant heat on all edges, which is written in the next form, not T, but U. We decide that U is our function that describes how our heat transfers initially it has like at x0, this x1, at x0 it has some constant temperature T0, and at final position it also has constant T0. Or we can't give any constant temperature. Let's for now use like symmetry. We are heating up both sides, and the heat transfers like this. By Fick's law, it's moving from hot place to cold. Next, we have Newman's boundary condition. What it says is, suppose our system has already some amount of temperature, and instead of heating them up, we are insulating both x0 and x1 boundaries. It means we have there no rate of heat change. So our heat will dissipate slowly and will cool down. Like it will just cool down. The heat dissipates. It's written in the next form, like rate of change at the boundaries. X1. Oh well, I should run as x0, x1 is 0. Like there is no flux. Flux means flow. Well, flux describes how fast the hot moves to cold. It's like how fast something flows in and flows out fast. Oh, sorry. So we have next condition called mixed. When we heat up some part, we insulate some part, and another part heats up. It's called mixed. In 2D case, for example, we have 4 boundaries. You can heat up some boundaries or insulate. Oh, sorry, I pressed Ctrl S. Next, let's derive the computational form of our heat equation to simulate them on programming language. From numerical analysis, well, numerical analysis, we can, well, maybe you remember that you can write ut as this in this form. So in numerical analysis, we can approximate our partial derivatives by t in the following form. It will take a lot of time to explain what's happening here, but please stay with me. Maybe in future videos we'll cover some basics of numerical analysis and learn how to discretize by using meshing, grid mesh. We can approximate our double derivation by x in the following form. N by x squared. What we are doing next is putting our approximations into here. Oh, let me denote this as equation number 1 and denote these two guys as equation number 2. So we are plugging in the equation number 2 into equation number 1 and get the following form. In t is alpha ui plus 1 and minus I2 ui and plus ui minus 13 delta x squared. So here let's express un plus 1. It's going to be like this, 1 and this un and extract delta t plus uin. if we draw, for example, a graph, since this is 1D case, actually I can draw like z-axis here and x-axis here. We have some system. What we are doing here, we are dividing our system to n amount of times. Like we have there infinitely amount of points, and we can't count them everything on our computer. So we have to discretize our time and position spaces. I'm discretizing them to n amount of times. Like this is some delta t. This is 2 delta t, and so on, and all n delta t makes me this whole axis. I hope you're understanding. We'll cover it deeply in future videos where I'm explaining how to discretize the system. So we discretize our system, and what we are doing next, we have to compute the u function at these nodes, at these intersections, because we can't compute this node because we don't know the t at this interval, at this point. Same for x. To compute the values in these areas not intersect, we have just to increase the amount of n, like this, to make our computation more accurate and precise. So let's start from u0. This is our first iteration. We found u0, it's given. Like it's usually a boundary condition, Newman or Dirichlet's. And now let's find the u1, 2. To find u1, 2, no, actually let's find u0, 2. Actually, since this is the origin, you have to start from 0. To find u0, 2, we need to plug in our u00 to here. Since our u-1 doesn't exist, we use it as 0. Oh, actually, this is a bad case. Maybe we'll start, I don't know, from here, because it's so hard for me to explain what's happening. This is u1, first iteration. We want to find u2. Yep, u2. No. 3. Maybe I'm doing something wrong. Okay, I couldn't explain this, but just know that to find this dot, we need this and these dots. To find this dot, we need this and these dots. So these dots, the shift to the right, like by t, is given by n+1, and shift to the by position is given by index I. So we are just computing these dots by using previous knowledge. And now we will simulate this on VS Code, on Python. I'll show now. Oh, and I forgot to mention that in high dimensions, in n dimension case of heat equation, everything is derived in a similar way. Just we have to find double derivation, partial derivation by each position, and sum them up. And to compute them numerically, here we know that partial derivation of u is used by delta x squared, and here it will be just division by delta y squared. Same for delta n squared. Well, we used n as dimension, maybe it it will be tilde n, like its position, not number of dimension. So here it is. We covered some theory. Now let's watch some simulation. Here I didn't have much time to use like terminal input for our model, but you can change the parameters here. So alpha is diffusivity coefficient, more is diffusivity coefficient, the heat transfers faster and more distributed uniformly. Like let's run. Actually, I've run it before for when I was repeating my video recording. So you see, this is our rod, and at at position 0 and 100, we are giving heat of 100 Celsius, and our rod itself is initially 20 degrees Celsius, 20 degrees Celsius. See, it starts from 20. I use 20 to show that how it cools down in Neumann's boundary when we don't give a heat. So at time t it's 20, and as time increases, for example, at time 2 and 4 seconds, at position 40 millimeters of our rod, the rod will have approximately 65 degrees. Since this is trivial function, but as my professor used to say, it's trivial, guys. It's symmetric. Like here, like you see, it distributes uniformly. As time passes, it will distribute like step by step, slowly. And if we increase the diffusivity coefficient, for example, to 1000, you'll see that it will heat up like so fast, and so uniformly, like our whole rod will be constant, will have constant temperature of 100, which is cool. Yeah, I can make it smoother, I can increase the time, for example, to 10 seconds, I can increase the rod's length, like this. Well, since rod's length became too long, it will take a lot of time and temperature to become hotter. Okay, maybe let's return back to 50 millimeters. Like, oh, well, I gave too much amount of time and our diffusivity is too high. Let's see at low diffusivity. Oh, it's like again I gave too much time. Okay, let's return 4 seconds. You see, lower diffusivity, lower is distribution of heat, and this was the Hughes boundary conditions. Now let's look at Neumann's boundary conditions. To apply it in our code, we just simply put our boundaries as 0, not only the previous, but also the next neighbor also as 0. And let's just look. See, our temperature was 20 initially, but we insulated the both sides. There is no heat, so the heat will dissipate, and our system will cool down like this. Now let's watch the 2D case of Dirichlet condition when I give our system heat from all sides. Well, to be honest, the draw part was repeated a bit, but main thing is this computational model. Oh, let me show the computational model quickly. If I open the node, our nodes, here, where is my computational model? Here. You see there is UI, like next iteration equals to dt. Here's my dt, multiplied by coefficient inside the braces, divided by delta x squared plus the previous like nodes, array of nodes. Same for Neumann, just it has different conditions. In 2D case we do the same, like here I just used y squared and applied it here like plus inside these like two braces, but one by dx, next by dy, and I just draw them and see this beautiful graph. What it says, like 100 temperature is given as white color, and you see as time passes our system becomes uniformly hot. For example, if I increase the diffusivity time and maybe diffusivity correction and time a bit, it should become more white as time passes. Become more 100 degrees. Okay, let's check. It's becoming more and more like brighter. Our plate is becoming more constant, have 100 degrees. And suppose we have Dirichlet and Newman's condition mixed. Like, let me insulate the left and bottom parts of my system. Like, heat is given only from top and right sides, like here. So what will happen here? Let's see. Same, like to apply Newman's condition, we just have to show that there is no rate of change, like it's zero from left and bottom side, and the neighbor nodes, they don't have rate of change also. You see here we have no heat, it's insulated, and heat is given only from top and right side. And as time passes, our metal will have here our metal is more hot than here. Like there is some flux happening. The flux is moving from this corner to this corner, and we can see the gradient, the rate of change, how flux is moving. So yep, that's it for today. Oh, and here we can choose delta t, a random number like 0.00001 or 0.1 or just 1. We have to apply Newman stability analysis. Well, I understand that you guys maybe got tired from my boring lecture explaining this heat equation that you don't use in your real life. But if you are interested, I can explain why we are choosing like what is amount of TT to be our system to be stable in next videos, and maybe cover some numerical methods and numerical approximations, like why do these guys equal to these things, scary things. Well, that's it. Thank you for listening. I'm not forcing you to subscribe or do any YouTube stuff that other bloggers say, but I hope in the future maybe I'll get more comfortable recording my notes, lectures. I've dreamed to open my own math channel, like 3 blue, 1 brown, or the bright side of mathematics, or Numberphile. These channels help me a lot with my study.